In this part of Chapter 12, we're going to look at polar covalent bonds and nonpolar covalent bonds, define them and see how we could predict them, as well as polar and nonpolar molecules. Now, one thing that I have omitted from this chapter is hydrogen bonds. We will be looking at hydrogen bonds in a different chapter. All right. So so far we have talked about ionic bonding, which is the transfer of electrons, which creates ions, and then you have an attraction between ions. And so over on this illustration, it says here you have something that's completely ionic. The electron is transferred. And then we have on the other side of that sharing electrons. And so we've talked about a covalent bond where electrons are shared. And so that's kind of where there's a little bit of variation. We just talked about covalent bonds, but electrons can be shared equally, which they would call here, that's kind of like purely covalent. That's like equal sharing. But what we haven't thought of yet is that not all atoms share the same or have the same attraction for electrons. And so when they share, they don't always share equally. And that's something called polar covalent. Now, I'm going to define all these things on the next slide and have some more words surrounding polar and what we call non-polar, which is equal sharing. But what I want you to think about in this slide is that we have defined bonding. We've said, oh, they're ionic, they transfer, they're covalent, they share. But really it's what we call a continuum. That means it doesn't really stop. It doesn't have sharp dividing lines. It's very helpful for us when we predict and explain to create some dividing lines so that we can manage all of it. But in reality, ionic bonding then goes into an unequal sharing, which then goes into equal sharing. So it's more like a rainbow, like the colors don't stop. And so what we're going to look at is the covalent bonds in particular and what it means and how we can predict if something's going to share equally or share unequally. And then at the end of the video, we're going to use Lewis structures along with those ideas to see that even in molecules then, when electrons are shared differently, it has an impact on the molecule. So we'll look at that at the end of this. Now, well, in terms of the words, I'm not sure these words are really hard, like polar, nonpolar, but this is kind of a hard concept for some people to wrap your head around. So I'm going to try to break it down simply for us in introductory chemistry so we can start the process of understanding what this means. So the first word, here we go. The first word, electronegativity. Like what kind of word is this? But it doesn't mean something hard. You can see there the definition. It measures an atom's attractions for electrons in a bond. So there's, like I said here, when I kind of rewrite it, it tells us how much an atom wants the electrons that it's in a bond with. Like how much it's like attracted to those electrons. And not all atoms have the same attraction for the electrons that it's involved with in a bond. And so this electronegativity value gives us a look into that attraction. So this is a chart from my other textbook. The table in your textbook was a little harder for me to read and how they tried to make it three-dimensional. So I just pulled this one from my other one. Electronegativity values, which we see on this chart, are not something that you have to memorize. In fact, if you look at the tables that I will give to you for the exam that includes Chapter 12, you'll see there is an electronegativity chart on it. So to answer the kind of questions about polar and nonpolar bonds that we're about to do, we're going to refer to an electronegativity chart. But let's just kind of get our feet wet and look at these numbers. So it looks at first glance like a periodic table because it does have atomic numbers and the element symbols, but then under the symbols are the numbers, which are the electronegativity values. You see, whoops, I want to change my pen. You see right here. Oh, I thought I changed it. I didn't. Oh, goodness. My eye pencil was going crazy. Okay, so there's underneath. That's the electronegativity values. And on your screen, depending on how big the screen is, it's probably hard to look and see the numbers, where it might be helpful to look on Canvas at the exam packet. But the highest number is over here, fluorine. That's a 4. So that's the highest electronegativity value. We don't worry about significant digits or anything with these. It's just our numbers. And then the lowest are down here, which is 0.7. And if you remember the trend, remember as you go from left to right, you get the atoms are smaller. So you can see here the nonmetals in the upper right-hand corner are the smallest elements, as well as the ones with the highest electronegativity values. And in the lower left-hand corner, the larger metals, they have lower electronegativity values. Okay, so the higher that number, the more attracted that atom is to the electrons that it's involved with in a bond. So fluorine would have the highest highest attraction to electrons in a bond that it's with, and then the metals down at the bottom would have the lowest. Now I want you even to just, as we think about this, and how it all really connects together, it's not really separate ideas. We talked about that previously, that metals like to lose electrons and nonmetals like to gain electrons. It has to do with the energy to gain and to lose the electrons, but also here you see that the nonmetals have more attractive power for electrons in a bond. And so if that difference is so great, they don't even share anymore, they just take the electron. So it all fits together. All the trends, everything is not all separate little silos that you have to learn. These are all things that fit together to give a big picture. Now, I would like you also to look at this periodic table, and if we were in class, I would say, what is missing? Like, what is missing from this particular, if you look at it like a periodic table, and as you look through, other than numbers, I know there's numbers missing, but there's a whole column missing right here, right? The noble gases are not there. Well, and that's because this chart is not a periodic table. It's an electronegativity chart, and noble gases don't have electronegativity values. Now, I want you to think before I answer it, why would they not have electronegativity values? Okay, well, let's look at the definition. The electronegativity is a measure of the atom's attraction for electrons in a bond. Okay, noble gases in general are not going to participate in bonding because they already are stable with 8 valence electrons. So the noble gases don't make it onto the electronegativity chart. They don't have electronegativity values because these are values that have to do with sharing, well, bonding. I don't want to say sharing electrons. It's bonding. So let's define polar and nonpolar bonds, and then let us see how we can apply this to the electronegativity values to the definitions. So here's the definition of the 2 types of bonds. So let's look first in red. There's polar covalent bond. Okay, so when this is going to happen, the atoms have different electronegativities. That means they have different attractions for the electrons in the bond. And here's an important idea about that. Polar covalent bonds, the electrons are shared unequally. Okay, that's because there's electrons between atoms, but they have different attractions. So the one that has a greater attraction will draw that electron cloud that's involved in the bonding toward itself, leaving the other with a deficit of the electron cloud. So here's an example of hydrogen and chlorine, and I want to go back to that electronegativity chart. Let's grab their numbers. So hydrogen is here, it's a 2.1, and chlorine is here, it's a 3.0. So I'm going to write it underneath it, 2.1, 3.0. Now, the higher electronegativity always has the greater attraction. So the electron cloud, they're going to be drawn toward the higher electronegativity. So in this case, they're going to be drawn toward the chlorine. Now, this illustration here tries to show you with a bulb. That's supposed to be the electron cloud. And if you notice, chlorine has a bigger amount of the electron cloud. That's because chlorine pulled the electron cloud toward itself more than hydrogen. Why? It has a greater attraction for the electrons. How do we know? Because the electronegativity of chlorine is 3, which is greater than hydrogen at 2.1. So a truth that I can say here is the atom with the higher electronegativity in a bond will always have a greater electron cloud. Now, how we notate that, what you might see are these little things here. I'll write it bigger. They use a lowercase Greek letter delta. So this is lowercase. Delta, the triangle we use when we subtract things, that's also probably spelled with a capital. That's also a Greek letter, but that's the capital one. Okay, so you might be familiar with that. But in this case, we're using, it looks like an S with a little squiggly. You can look at it online. And how I think of it, it means like partial. It's not a complete difference, it's a partial difference. And so we can have a delta negative, and you can see this time they wrote the negative in front of it, this time they wrote it behind it. It doesn't matter. You can have a negative one and a positive. So remember, electrons are negative. So if chlorine is pulling electrons to itself, it's going to become partially, or I always think about it a little bit, negative. That would leave the hydrogen a little bit positive. So a thing that I could tell you here is the higher electronegativity element in a bond always has the delta negative, right? Because it's always going to pull the electrons toward itself. And we're going to practice a few of these, but this is what we understand. Now, when you get that plus and minus negative, here's some words for us. We create a partial separation of the charge, which is called a dipole. So the separation of the charge simply means that there's a plus and a minus side. I feel like I'm starting to yell because I'm trying to make sure you understand. But there's always a plus and a minus side. That's just called a dipole. And that occurs when the electrons are not shared equally. So a polar bond is when two atoms having different electronegativities do not share equally. The atom with the higher electronegativity will pull the electron cloud closer to itself, creating a little delta negative, a partial negative. That leaves the atom with the lower electronegativity with a partial positive, or a little delta positive. When you have a delta positive and a delta negative, you have a partial separation of charge, which is called a dipole. A complete separation of charge is when you get ions, when the electron is completely removed. But this is just a partial separation. The electron's not removed. The cloud is just shifted toward one side more than the other. Now, in contrast, you can have nonpolar covalent bonds. And really, just using the word polar and nonpolar, you could omit the word covalent because polar and nonpolar are referenced to sharing. But to be specific, it is a covalent bond. So a nonpolar covalent bond occurs here in blue when the electronegativities are close to the same. So what the result is there's no delta minus and delta positive in a nonpolar. There's no dipole, which is the separation of charge. So when the electronegativities are close to each other, then the electrons are going to be shared equally. So polar is when the electrons are shared unequally because of a difference in electronegativities. Nonpolar bonds occur when the electrons are shared equally and occur when there's no or very small difference in electronegativity. So let's look. I have a summary chart. And I'm not going to pause it long enough for you to write everything down, but of course on a video you can pause and go back and do what you need. I got this from another textbook because I thought it was kind of helpful. And remember, it's a continuum, so like down here, it looks like it just goes from one thing to the next. That's called a continuum. Oops, I think I missed a U in that. What am I doing? Continuum. Two U's. Okay, sorry. So that's a continuum. So to help us when we're trying to organize things, we come in and we make some lines up. We try to draw some boundaries so we can classify the different bonds. And so this talks about using the difference between two atoms because we're talking about bonds here. And so we can subtract the difference in electronegativities, and then using that difference in those values, we can classify the type of bond that it is. So you can see here, nonpolar covalent, where the electrons are shared equally, the difference would have to be less than 0.5, so 0.4 or less. So we'll just draw a fake little line. So we would say, okay, here, this is 0.5. And so if you're below that, you're nonpolar. And I don't know where the lines really would be. I'm just trying to illustrate. And then 0.5 to 1.9, so then they draw some lines here, and then they say, okay, this number is going to be 1.9. And if you're anywhere between these two numbers, here to here, then we're going to call you polar covalent. And then if you get greater than that over here, then we're going to call you ionic. And then here's just how the electrons, and we've been talking about, covalent or shared. And so now and ionic or transferred. All we're really adding now is, are they equally shared, which is nonpolar, or are they unequally shared? So this is not a set in stone kind of difference, and you could come across different textbooks that I think one of my other textbooks only goes to 1.8 instead of 1.9. So you could come across other textbooks that have slightly different lines that they've drawn. But again, the lines are just to help us kind of imagine where the breakpoints would be or where the transition occurs. But since it's a continuum, it kind of moves from one process to the other. Now, I think, we're going to do some examples. But I think I need to just add something here. And that is, if the question only asks you, do two elements form ionic or covalent bonds? So if that's all it's asking, not polar, nonpolar, just ionic or covalent, then I want you to remember that ionic, we predict that for metals and nonmetals. And that covalent bonds, we predict those will occur, covalent, between nonmetals. So if the question is just asking you, is this ionic or molecular or covalent bonds, then we just look at the elements involved, and that's how we've classified it. This, when we use electronegativity values, this is really about getting into like more detail and trying to decide if the electrons are being shared equally or unequally within the covalent bond. So what we're about to do, the question has to do more with, is this nonpolar or polar covalent? So this is how we would do it, and I'll just pick two. Let me pick, let's see, I'll pick nitrogen and bromine. Okay, so I'm just looking at a bond. And so to use electronegativity differences, let's see, nitrogen I see on my chart is a 3. You don't memorize these numbers. Bromine is a 2.8. So you take the difference, and it always has to be a positive value. So whatever, it doesn't matter if the higher one is written first and what the bond you're looking at, it's always going to be a positive. So take the higher of the two values and subtract the lower, and this we get 0.2. Then if you look back on the previous slide, less than 0.5, that is nonpolar. And so this type of bond is not a nonpolar bond. Okay, I'm just going to write less than 0.5 is nonpolar. I'm going to write it on here. What did they say? 0.5 to 1.9 is polar, and greater than 1.9 is ionic. Okay, so that's an example. Let's do another one. Let's say we have hydrogen bonded to oxygen, which is really common in biological molecules. So let me erase these two circles. So oxygen is here. Oxygen is a 3.5. Hydrogen is here. That's a 2.1. Remember, we don't have to memorize these numbers. So always use the higher. So 3.5 minus 2.1 equals what? 1.4? So 1.4 is polar. Okay, so this is a polar bond. Now, I will tell you, when I ask you about polar bonds, I always ask you to draw which side is negative and which side is positive, the little deltas. So remember, the electrons always go toward the higher one. So the negative would always be the higher one. So in this case, you would have a negative over the oxygen. Ooh, my delta did not work very well with it goes this way. Negative here, and then a positive here. This has a dipole. So it's always the higher electronegativity gets the negative side, and the other one gets the positive side. And I do ask you to do this. So when you answer questions like this. Let's see. Let's find another one. Why don't I say sodium and chlorine? And I hate even drawing a line because this I know is ionic. But sodium is 0.9 and chlorine is 3.0. So 3.0 minus 0.9 is 2.1, which is greater than 1.9. So this is ionic. And there's no plus or minus here, no delta plus or minus, because this is ionic. We know that the sodium is going to lose an electron completely to the chlorine. So there would be no little delta pluses or minuses. What happens if there's two of the same? Let me erase some of my circles just so we can see better. So two of the same. Let's say I have a carbon and a carbon. Okay, so carbon is right here. It's 2.5. 2.5. Well, 2.5 minus 2.5 is 0. So this is a purely covalent. This is a non-polar covalent bond because it has 0. So if they're the same, it's not no bond. It just means that they share completely equally. Let's see, another one. Well, I think let's do another polar one. So let's say let's say I have hydrogen with fluorine. So fluorine is the big one. So 4.0, hydrogen is 2.1. So let's see, that is 4.0 minus, look how close. This one is 1.9. Like this is on the edge of being ionic, right? Because it's right there. So let's see, but it's 1.9, which is still in the boundary. So this comes this way, so the fluorine would be definitely negative, and the hydrogen, oh, let me write that in a different color, because that's the dipole. The fluorine would be definitely negative, the higher one, and then this would be definitely positive. So that one's on the edge like that. And in reality, maybe what I think happens is that it probably has some ionic type characteristics, because it's getting close to where the difference is so great. So, but in terms of how we're defining it now, it would slip in to the polar. So what we're doing right now is what you would do if the question asks you to determine if a bond was nonpolar covalent, polar covalent, or ionic. And I'll write that down for you. Okay, so that's what we were doing here. And so now we're going to switch gears, and we're going, or add on to our gears, add on to our machinery. And we're going to say, okay, let's think about a molecule now, because molecules, what we're doing here just looks at one bond. But molecules have multiple bonds together, and how does it all impact each other? Oh, I thought we were going to do that, but I have one practice for you, which is kind of hard because you've got to know the electronegativities. So let's go, and I'll help you find them, and then I'll let you answer the question. Okay, so let's see. Beryllium. Well, I know fluorine is a 4.0. Beryllium. What's beryllium? Oh, gosh, I wrote on it. I think it's a 1.5. I'm guessing. I know this is a 2.5. No, 2.1. Sorry, and a 3.0. I think sodium might be a 1? Let's look back. Sodium is a 0.9. Oxygen's 3.5. And fluorines are both 4. All right, so you can pause it now. Now, those numbers you don't have to have in your head. You'd have a chart. I just didn't put a chart on this slide, so I apologize for that. If you have a chart by you, you can verify. So go ahead. They want a polar covalent bond. So between which ones? Go ahead and pause it. I'm going to give you the answer because I don't need to pause the video for minutes of silence. Okay, so I can see which one, but how you would do it is you would go, if you weren't sure, you would just subtract. So what is this, 2.5? Okay, so that's ionic. And here's the one, right? 3 minus 2.1, which is 0.9. Okay, so this is the one. This is polar. So I'm thinking it's B, but we'll double check. 3.5 minus 0.9 is what, 2.6? Is that right? Okay. 2.46, right? I don't know why I can't subtract. Well, I'll tell you, I'm feeling kind of tired, so maybe that's why. 3.5 minus 0.9, 2.6. Okay, I'm not as off. Ionic, and then 4.0 minus 4.0 is 0, and that's nonpolar. Okay, so that's how you're thinking about answering this question. Is you're subtracting the difference to see which one falls into the range of 0.5 to 1.9. That's the polar one. So it would be letter B, hydrogen and chlorine. Okay, now we're going to look at molecules. So the thing about molecules, so on this slide, this is cancel. On this slide, you don't have to worry about, I'm going to give you some steps just to think about a Lewis structure. You don't really have to worry about what they generally have. It is just kind of to start with a picture. So molecules also can be classified as polar or nonpolar. And it not only depends on what bonds they have and the polarity, but it depends on their shape. So it depends on how the bonds are oriented around that molecule. Now, if we were to really calculate if a molecule was polar or nonpolar, we would use vectors. And you add them and subtract them and like put them all together. But we don't have. Okay, this might be a repetition, so I need you just to know. Someone called while I was making this video. It stopped the recording, but now it's letting me pick up again. So I'm going to probably be repeating some of the things I was in the middle of saying, but I would like to make sure I'm not quite sure where it cut off. So I want to start with polarity of molecules. So I'm sorry if you have to listen to me talk twice. So what I was trying to communicate is when you have a molecule and it has bonds attached to a center atom or whatever, we have different polarity of bonds, and those polarities, as well as the shape, determine if the overall molecule is polar or not. Now, and so I mentioned because I used the dreaded word vector. So if we were going to do this with a calculation, we would use vectors. And if you don't know what vectors are because you haven't done that in math yet, 100% okay, because we don't have to do vectors. I'm going to give you some questions you can ask yourself about Lewis structures to determine the polarity of a molecule. Now, before I do that, and before we look at it, I want you to know that when we talk about molecules, the word polar and nonpolar really do mean the same thing. So nonpolar means that the electrons are distributed and or like the electron cloud is distributed evenly. And I don't want you to think that that means they each have the same number of electrons or anything. It's the cloud where the electrons are. So it's got a nice even, or if it helps you, again, because nonpolar means equal, if that helps you to think of that, it means it's like equally or evenly. And so the result is that there's no partial separation of charge, which we call a dipole. So there's none of the little delta positives and delta negatives that's caused when the electrons are not evenly distributed or distributed makes me feel like I doled them out and everybody gets the same amount, but it's about the cloud and it being even. Polar, just like in bonds, polar means that something's unequal or uneven. And so in this case, the electron cloud, because of how the bonds, their different electronegativities and their polarities, as well as the orientation of the electrons and bonds around the atom, they are distributed unevenly, or you can think of unequally. And so anytime your electron cloud is not even, you get electron cloud more in one place than the other, and you get a dipole. So then the molecule itself will have positive parts and negative parts. So you don't have any of that up here. Now, what the big picture of this is, and we'll think about it more when we're talking about solubility and things, but big picture, when you have something that has even a little bit of positive and negative, it interacts with things differently. Because remember from ionic bonds, like charges attract, opposite charges repel. So molecules that have a plus and a minus, the dipole, they will attract to each other, the pluses and the minuses. And so you get interactions between molecules that have dipoles. So it's important for how molecules interact with each other if they're nonpolar or if they're polar. And so we'll see polar and nonpolar molecules in the future. Now, I did mention that you don't have to, well, I want you to know nonpolar and polar, but you don't have to memorize these things. These are just some general characteristics, like nonpolar molecules. They may have no polar bonds. That would make everything equal. Or they have polar bonds and they cancel each other out. That's where the vectors come in. Polar molecules usually have at least one polar bond, or how they're oriented, the bonds, their dipoles don't cancel each other out. So that's just kind of in general why it's happening. But again, I have several questions that you can use Lewis structures for and ask the questions to decide if a molecule is polar or not. And with experience, looking at different molecules, you will become more familiar when you look at them as to whether you suspect them to be polar or not polar. So let's look at the questions and then apply them. Okay, so these are the questions that we're going to use. It is based on seeing a Lewis structure, and I have on the next slide, I have some Lewis structures that will apply. I do find that it's easiest to ask the questions from the top to the bottom. Really, these two questions here, the last two questions are very connected. You really answer them at the same time. So the first thing we want to do when we look at a Lewis structure, if we're trying to figure out if the molecule is polar or not, is we want to see if there's lone pairs on the central atom. And if there are, that molecule is polar. Lone pairs are I always think of like a big dollop of negative charge. And so it makes the electron cloud around that atom be unequal. So we're going to look for lone pairs on the central atom. Then the next thing, if there's no lone pairs, then you have to think, okay, so now I look at other things. And so now what you're going to look at are the atoms that are on the periphery. So it says, are the atoms attached? So what we're talking about here, these are the periphery atoms. Remember, we introduced periphery as a part of Lewis structures. They're the outside atoms. And what we're really trying to identify here, are those atoms the same element as each other? Not as the central atom, but as each other? Or are they different? So it says, are the periphery atoms attached different elements? And I want to say from each other, not from the central atom. So if they're different, then the molecule is polar. If the elements on the periphery are the same as each other, not the central atom, then it's nonpolar. Okay, and it doesn't matter if they have single bonds, double bonds, triple bonds. So let's go through the questions and then we'll try. If there's lone pairs, it's polar. Okay, then you're done. Okay, polar. If there's no lone pairs, then you look at the periphery atoms. If the periphery atoms are different from each other, not from the center, but from each other, it's polar. Really, if you think about it, it's because if they're different, they're not all going to pull the electron clouds the same, and so you end up with positive and negative. If the atoms are all the same from each other, are the same as each other, as each other in that example, not from each other. Would make more sense, huh? They're the same as each other, not as the center, but as each other, then it's nonpolar. Because what happens, even if they're polar bonds, they cancel each other out. Their effect cancels each other out because they're all the same. Something, as you go into larger molecules, what you're going to find is really electronegative elements. And I'm talking about things like nitrogen, oxygen, and fluorine. They cause large molecules to have some polarity. Here's another really cool thing we'll talk more about when we get into solubility. But some really large molecules, the whole molecule isn't polar. Like they can have parts of the molecule that are polar and parts of the molecule that are non-polar, and they like can do different things. Like they don't separate from each other. They just interact with what's around them differently. So we're looking, these questions really apply to smaller molecules, and that's what we're going to be trying to answer. But we'll try to think about like bigger molecules as we get a little bit later into the class. So let's apply the questions. So I have 3 examples. Okay, so the first question, I'll have to go back and forth. The first question is, are there lone pairs on the central atom? And if the answer is yes, the molecule is polar. So I look at the central atom, okay, there are, and I'm just going to write my thoughts here, there are no lone pairs. Okay, so that is the first question. Why did I write no lones? Okay, lone pairs. Okay, that's the first question. Okay, so we got a no. So now I got to go to the second and kind of the third question together, I think. And I say, are the atoms attached to the central atom different from each other? If so, it's polar. Are they the same as each other? Then it's nonpolar. So I look and it's chlorine, 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 chlorine. So they're the same as each other. So this first molecule is nonpolar. And when you do it yourself, when you're first learning, it might take you longer. But if I looked at this one, I'd say, okay, no lone pairs. They're all the same, nonpolar. Like the out periphery are all the same, nonpolar. Like once you get going, you don't have to talk to yourself as much. Okay, let's look at another one. Let's look at the second one. Okay, so I look at the center, and the first question is, are there lone pairs? Okay, no lone pairs. So that means, okay, now you've got to go, that question is no, you got to go to questions 2 and 3. Are the elements the same or different on the periphery? Okay, so this one is oxygen, hydrogen, hydrogen. So these are different. I mean, I know there's 2 hydrogens, but then there's an oxygen. So they're not the same as each other. There's a different element, and it only takes one. And so in this case, they are different. Oops. And so this is a polar molecule. Now sometimes, and in this case, we really can see it, what's going to happen. So if I look at electronegativities, and I know these electronegativities, you don't have to know these. I just do, just from doing this so long. But I just want to demonstrate something. So like this is a 2.5, and these are 2.1s. This is actually, these are kind of non-polar down here, but this is a 3.5. And so what happens is the electrons on the electron cloud really wants to go to this oxygen because it has higher numbers than the other ones. And so what ends up happening here is the oxygen becomes negative, and down here it is more positive. So this side, it becomes the more positive side. So you can't always see it so easily, but in this particular, it's a trigonal planar molecule. You can kind of see how the oxygen might pull the electron cloud toward itself more than the others. And that's what it means to be polar. And finally, water, which is the one I emphasize the most, and I will ask you questions about water, questions about its polarity. If you're listening to this video, you probably are going to get this question. If not on this coming up test, you'll get it on the next test about the polarity of water. So it's pretty easy to see with the questions we ask for ourselves. The first question is yes, there are lone pairs. And so this is a polar molecule. So that's one thing I want you to just memorize, is that water is a polar molecule. And even more importantly then, I want you to know what part of water is the negative side and what's the positive side. And this is another one we can kind of look at the bonds. It's set up that way. We've got the lone pairs on the top, but also looking at the electronegativities. Oxygen is 3.5 and these guys are 2.1. And so for both bonds, the oxygen is going to pull the electrons toward itself. So oxygen has not only electrons with lone pairs, but also has higher electronegativity. So as a result, the dipole is the oxygen is negative, and down here the hydrogens are positive. And it's not two positives to one negative. It has to all balance. So let me show you two ways, like if you're asked to draw that. So sometimes I just see people just put the negative up here and then the positives down here, because the oxygen's negative and the hydrogens will both be positive. Again, it's equal, but that is, like, you're not going to have extra negative or extra positive. They cancel each other out. The other way, when they're drawing the dipole, is they may just draw an arrow up the middle and put the negative here and then the positive part down here. So either way, they both represent a dipole, right? Because that's what it means to be a polar molecule. It's the dipole. You have the separation of the charge. All right, so that is polarity. Don't feel bad if you feel like, oh, I got to sit with this a little bit, because that's how polarity is. I don't know why, but that is how it is. So it's okay. Anyway, always feel free to ask questions in class.